So after seeing the pre-order, post-order and in-order traversal in our tree, now we will see the height and the size of the tree. Okay, so how you will calculate the height of tree using recursion and size of tree using recursion. Fine. So what is the height of the tree is? It is nothing but the height of the root. And what is the height of a root node or any node is the number of edges between the node and the leaf node. Okay, the number of edges between the node and the leaf node. So here the number of edges is nothing but 2. So height of this left side is 2 and the height of right side is also 2. So since it is same, so the height of this tree becomes 2. Okay, now for example, if I change the height to here 9, that is I add one more element, so the left side tree now becomes, so the right side tree now becomes 3, the height becomes 3. So the maximum of these two is taken as the height of the tree, so we have 3. Okay, so what you have to do is you have to calculate the left side tree, height of the left side tree and height of the right side tree. Okay, and whichever is maximum will be my answer. Whichever is maximum will be my answer. It is that simple. Now as you can see here, it is 2, 4 and 5. So this is my left side tree. Here also you have to do the same. Calculate the size of the left side tree, height of the left side tree and the height of the right side tree, and whichever is maximum will be the height of 2. Correct, and it will return that height to 1. Only there is a slight change here is that we will not return 2 and 3 here. We will return actually 1 and 2 here, not 2 and 3, but we will return a -1 value. Why we will return a -1 value is I will simply tell you that after writing the code. Okay, when I am explaining you the recursion stack for this, at that time I will tell you. Okay, just remember that when we are at the leaf node and this function calls with the help of a null value, if my node value is null, it will not return a 0, but it will return a -1. It will return a -1. Fine. The reason being here why it will return a -1 is in our code we have a function. We'll calculate the left height also, that's right. We will calculate the right height, that is also right, and we will compare. If left height is greater than right height, we will return left height plus 1. Okay, else in all the other cases we will return right height plus 1. Fine. Now to balance this plus 1, we are going to return this -1. Fine. Now why we are doing this, I am going to explain you the same concept again in recursion stack. Okay, but first let's write the code for this. Okay, the code is same. Just calculate the left height, just calculate the right height, and just compare this. And after that I am going to explain you the recursion stack for this one, and there you will simply understand it. Okay, and the size of the tree is a very simple code. It is the same as the height of the tree. Instead of comparing the left height and the right height, what you have to do is you have to add the left side number of nodes and the right side number of nodes. Okay, because the size of the tree is the total number of nodes in my tree. It is nothing else. It is very simple. So we will concentrate on the height, and you can do the size one also. Okay, I will tell you the code for the size. Okay, but you have to do the recursion stack for the size on your own. I will explain the recursion stack for the height too. Correct. So now what I'm going to do is I'm going to write the code for the height of the tree. Okay, so here just write the simple code for the height of the tree is, that is int height of tree, and pass the node. Fine. So if my node is null, if node equal to null, return me a -1, return a -1. And if the node is not equal to null, then what you have to do is else calculate the left side height, the left height. Okay, calculate the left height. That is how you will calculate the left height. Just call the same function with the left subtree. So the node dot left. Okay, node dot left. How you calculate the right height is int right height equals to height of tree node dot right. Correct. So we passed both the left subtree also and the right subtree also. Now if my left height is greater than my right height, just return left height plus 1. Fine. And else return right height plus 1. Okay, right height plus 1. Now why this plus 1 and -1? Now I'm going to explain you. This is a simple code. We calculated our left height, we calculated our right height, we compared the left height who is greater, and whichever is greater we are returning that. Fine. Now I'm going to explain you why this plus 1 and -1 is taken using the recursion stack method. So this is my tree, correct? And I am going to find out the left side height and the right side height, and I am going to compare them and return +1 to each of the values. Now why I am doing that? So my first call will be to the function while passing the root value, correct? So node equals to 1. This is the first step. Okay, it will be done with the parameter only. The first step is checking whether node equal to null or not, which is not, so it will not run. What is the second step? Second step is calculating the left height by passing the node dot left. What is node dot left? As you can see, the node dot left is nothing but 2. Okay, so now the function will call. The function will call simply. Now the same function with node value is 2. Correct. The first thing is not equal to null. No. Now what is the second point? The second point is the left height of this subtree. Now this left height of this subtree, that is called 4. That is called 4 because 2 of left is 4. Correct. Now we will call 4. Now while calling 4, what will happen is the node becomes 4, and the first is again false, and the second is calculate the left height of 4. So is there anything with on the left or right of 4? That is no. Therefore it will pass simply a null, and when it passes a null, what will happen is for null it will return me a -1 value. For null it will return me a -1 value. As you can see here, if the node is null, it will return a -1. So the left height will become nothing but -1. Correct. And the right height is same, call null, because there is nothing to the right of 4 also, and it will return a -1. Correct. Both are -1. Now we will compare if left height is greater than right height or not. No, it is not. So we will go to else, and we will return what we will return. We will return right height plus 1, that is -1 plus 1, that is 0. So this 4 will return 0. Okay, so for 4, all the 4 steps are over. We only have 4 steps, and for the node 4, all the 4 are over, so it will return to the parent node, okay, to the calling function. So where it will return here. So the left height will become a 0. Fine. Now you would be thinking, but the height is 1, why we are returning a 0? Now you will understand, in a short bit you will understand. Okay, this is the suspense in this question. So now for the 2, left height is over, we will calculate the right height, and the same thing which happens with the 4 happens with the 5. Now you have to do the recursion stack for 5. As I have done this, you have to done this for 5. Okay, and it will also return a 0. I am telling you the answer, it will return a 0. Fine. So it also returns a 0. Now you will again get confused. It should be a 1. Why it is a 0? So I will just explain. It will come. It is a suspense in this question. Okay. So it is a 0. It is also a 0. Now it will compare. This is the fourth step for node 2. So left height is greater than right height? No, false. So it will go to else. What it will see it at else? That is return right height plus 1. What is right height? 0. 0 plus 1 will be returning a 1. So 2 will return a value of 1 to the node 1. Correct? So now it should have returned 2 because the height is 2, but it returns a 1. It does not return a 2. So it returns a 1. So left height becomes a 1. So left height becomes a 1. Correct. So now calculate the right height. So call 3. For the node 1, calculate the right height, call 3, and do the same process again. You have to do the same process. I will not do the same process again. You have to do this. So the right height becomes call 3. Okay, and it will also return, say 1, 2. So it is 2. So it will return me simply a 1. So it will also return a 1. You have to do this and cross check whether it returns a 1 or not. So both returns a 1. Now you will understand. Now the suspense will clear. Okay, we are at the climax. So the left height is greater than right height or not? No. So we'll go to else, and it will return a right height plus 1. So right height is 1, and 1 plus 1 will give me a 2. So actually, in actuality, the root node will return 2. Okay, it got 1 from both the sides. Okay, it should have gotten 2 from both the sides, but if he has gotten 2 from both the sides, then what will happen is that it will add 1 to that 2, and it will return a 3 value, but that would be wrong because the height of the tree is nothing but 2. Correct. So 1 plus 1 will become simply a 2, and it will return me a correct answer. So to manage this extra 1 that we are having here, to manage this 1, we are returning a -1 at the end. Okay, to manage this 1, we are returning a -1, and there is nothing else. This was the suspense here. Okay, so here we have a 1, we have a 1. So since both our value are 1, so 1 plus 1 will simply return a 2, that is the height of the correct height of the tree. Correct. Now what I am going to show you is I am going to run this program, and after running this program, I will change this value to 0. I will change this value to 0, and you can see the difference with your own eyes. Okay. Now these types of experimentations you should do it by your own. Okay. Whenever you think why this value is this, and it should be 0, it should be 1, or it should not be plus 1. So just do these experimentations yourself. It is very simple to do these experimentations. Okay. Now I'm going to simply call tree height of tree, and I'm going to call node. I'm going to call tree of root. Okay. Now you can see the height of the tree that we are currently using, that is 1, 2, 3, 4, 5, 6, and 7, is nothing but 2, and the answer will be 2. Okay. There is no doubt the answer will be 2. See, as you can see here, the height of the height traversal is 2. Okay, just change this height of tree, not height traversal. Height of tree is 2. Okay, now I'm going to show you, if I change that -1 to 0, what will happen is it will not balance that +1 at the end. Okay, and the +1 will win, and what will happen is I will get my answer, instead of 2 I will get my answer as 3, because the +1 is extra at the end. Okay, as you can see, the answer now becomes a 3. Therefore, to balance it, I am going to use a -1 here. So it was that simple. Now what I want you to do is, I want to write the code for the size of the tree. I want you to write the code for the size of the tree. Okay, obviously I'm going to write it. Just pause the video and write the code for the size of the tree. Okay, it is very simple, and it is very small also. What you have to do is, in size of tree, what is the size of tree? The number of nodes in the tree is the size of tree, correct? So here, node, here what we are doing, we are calculating the left height, and we are calculating right hand, and we are comparing it. There what you have to do is, in the size of the tree, all you have to do is calculate the number of nodes on the right side and the left side and add them. Just simply add them, and it is done, it is over. So let me explain you this with the help of a diagram, and after that I will write the code for it, but you have to write the recursion stack for this. Now for this one you have to write, I have shown you 2 times how to draw a recursion stack, but this, for size of the tree, you have to do this. Okay, so what will happen with the size of a tree is, you have to calculate the number of nodes, the total number of nodes. So calculate the number of nodes on the left side of the tree, calculate the number of nodes on the right side of the tree. Okay, so the left side number of nodes equals to 3, and the right side number of nodes equals to 3. So 3 plus 3 will give me a 6, but the final answer is not 6 but 7, because do not forget we do have a root also. So when you are returning your answer, what you have to do is right hand side plus left hand side plus 1, and this is your final answer, and it is done. So why it is +1? This +1 is because we have to consider the root also, correct? Now just write the code. Now it's very simple. Write a simple code for this. Okay, so what we will do is, this is the size of the tree, and if node equal to null, then return a 0. Okay, here we do not need to balance anything, and else just simply do this. Okay, int left size, or you can say the left number equal to size of tree on the left hand side. So node.left, and the same thing you have to do for the right hand side. Now I am doing this question in 3 steps, but this question is actually done in a single step. Okay, so right, in the else we should have written only one, in the left we should have written only one line. Okay, but for your simplicity I am writing 3 lines. So size of tree node dot right. Okay, and finally just return me the left number plus a right number plus a 1. Okay, now I could have written all of these things in a single step like this. Okay, what the step was, return, instead of storing each time, just return size of tree in the left side, okay, plus size of tree on the right side plus 1. Okay, this would have done this. Okay, but just for your explanation, because the 3-line approach will give you a more clarity when you draw a recursion stack. Just draw a recursion stack. Okay, don't skip it. Draw the recursion stack. This is very important. Okay, now this will give me the final answer. Just call this function from the main. So when I call this, it will be simply a system.out.println size of tree is plus just call this tree dot size of tree. Okay, and pass tree dot root. So this is done. The size of tree is done. I want to write the size of tree recursion stack for this one. Okay, the size of tree is 7. So we have done with the height of the tree, we are done with the size of the tree. The only homework is write the recursion stack. This is very important for recursion. When you write a recursion stack, what will happen is all the recursion doubts will get cleared. Okay, how the functions are calling, where the function value will return, how so many functions call will be handled. Recursion stack will clear every point for recursion. Okay, so just write it down. Now we have seen pre-order also, we have seen in order also, post order also. I have given you a homework for in order and post order too for the recursion stack. There is a reason I am telling you to draw a recursion stack, because it is important. Okay, just draw a recursion stack and you will understand it. Fine, why it is important. Now size of the tree also, you have to draw a recursion stack for this. After this we will simply do a level order traversal. Okay, and that will end this. Fine. So we will also do in the same program, we will write one more function for level order traversal. Okay, now we are going to see level order traversal. So what is level order traversal? So 1 2 3 4 5 6 7, this is level order traversal. So this is a level 0, this is level 1, this is level 2. So all the nodes at level 0 will first, it will print. All the nodes at level 2, level 1, it will print. So 2 3, and all the nodes at level 4, it will print 4 5 6 and 7. Okay, so this is level order traversal. Okay, first on the one level it will print everything, then it will go to the next level, it will print everything, and it will go to the last level and it will print everything. Okay, now you could see a similarity here. Just see this one. What we have done is we have added 1 2 3 4 5 6, and the same order which we have added, it is returning me the value. Okay, 1 is added, then 1 is returning, then 2 is added, 2 is returning, 3 is added, 3 is returning. So the first one, first in was first out. Okay, 1 was the first one in and 1 is the first one out. As you can see, 2 is the second one in and the 2 is the second one out. So it is following FIFO order. Now you have reached till 3, and you should know whenever FIFO is coming, there is a data structure which is used, that is Q. For the FIFO order, mostly Q is used. So we will also be using Q for the level order traversal. Now, since this is a tree and collections are not done, we will not use the inbuilt class of Java Q. Okay, what I have done is I have written the own code for Q implementation, and it contains all the operations, that is NQ, peak, DQ and everything. Okay, what you have to do is you also have to write your own implementation class for Q, which contains NQ and DQ. Correct? NQ, DQ, peak, is empty, those main functions it has to contain. Fine, you have to write your own implementation of class of Q, and I will be using that implementation class in my code. So how it works is, in a queue, first it will go to level 0, that is a root node, and it will fetch it. It will fetch it from this and it will add it into a queue. So I'm using the array representation for the queue, so it will add it into my queue, that is 1. Correct? Now what it will do is, after it adds into my queue 1, what it will do, now it will add its childs. It will add its child, so it will print 1 and it will add the child of it. So 2 and 3, the left child and the right child, so it will add 2 and 3. Okay, now what will happen is, first we will dequeue 2. Now since we are at 2, we will dequeue 2 and we will print it. Okay, now when we dequeued it, we store it into we will store it somewhere. Okay, when we dequeued it, we will store it somewhere. Okay, and what we will do, we will add the childs, we will add its child. So 4 and 5 will be added. Okay, the child of 2. After that 3 will be dequeued, it will be printed, and the child of 3 will be added, that is 6 and 7. Okay, after that 4 will be dequeued, it will be printed, there are no childs to add, so nothing will be added. After that 5 will be dequeued and it will be printed. After that 6 will be dequeued and it will be printed, and finally 7 will be dequeued and it will be printed. As you can see here, we will have 1 2 3 4 5 6 and 7. So first NQ from here and then DQ from here. So NQ1, we have NQ'd 1, DQ it, print it, add its child. Okay, DQ2, print it, add its child. DQ3, print it, add its child. So 3 operations. First we have to NQ it inside our queue. After that DQ it, print it and add the child. Okay, DQ, print, add child. Okay, we have just 4 operations: NQ, DQ, print, add. NQ, DQ, print, add again. So these are the only operations. Actually we have 3 only: NQ, DQ, again NQ. We have 3 only. The add is NQ only, no? So we have only 3 operations. So this is also easy, you can try it. Okay, I wanted to try it, and this is also not what you say a recursion. Okay, and this is also not a recursion, so it is just iteration, though there will be no recursion stack in this. So just try it. I've told you, first you have to NQ from here, you have to now DQ, print it, and NQ its child. Okay, NQ both the children's. You can do it, I think. So I will just write the code for the level order traversal also. So before writing the code, just pause the video, write it yourself, then cross check it. It will be good, it will give you immense pleasure, it will give you immense confidence, and even if it is wrong, it will give you some satisfaction that you have tried. But if you haven't tried, it will not give you any type of satisfaction. Fine, so I want you to try it. Just please try it. Traversal node key. Okay, let this time be instead of a node, use a key. So if key is null, if key equal to null, what will happen? Return. Just return nothing, just simply return. Okay, return. After this, what will happen is we will use the queue implementation class that I have created. Now you have to create your own implementation of class of queue. So this is the implementation class of the queue that I have created. As you can see, I have my everything, the node and everything, the queue, dequeue, everything. So I'm not going to show you that. Just what you have to do is write your own class. Okay, so I have used a queue implementation class of my. So I will use that class. I will use a reference variable for it, queue. Okay, this is simple reference variable equals to new queue implementation. Fine. And I will pass the size. I will pass it is asking for the size, so I will pass the size of the tree. So how you will calculate the size of the tree? So just call this function, okay, to calculate the size of the tree. We have seen this, size of tree, so you can call this function also. Okay, in this case I know the size of the tree is 7, so I will just pass a simple 7 here. But what you can do, you actually not what you can do, you have to do, just call this size of tree, okay, and pass the root node, and it will be done. Fine. Or else let me just write it, or you will say the sir is lazy. So just size of tree and pass the root, now you do not have to use tree.root because we are in the tree traversal class and the root is in the tree traversal class, so you can directly use it. Okay, now what you have to do is you have to enqueue. Inside the queue. So what is the first thing you have to enqueue? That the root that is part, that is key. Correct. So enqueue key, sorry, queue.enqueue and key. Correct. Now we enqueued the key. Now the next thing what we have to do is while loop. So this is not recursion. So queue, while queue is not empty, so is empty. If it is 2, it will become false, and we will move ahead. Create a node to store what we will dequeue. I told you first we will enqueue it, we will dequeue it, we will print it, and we will again enqueue the childs of it. Correct. So what we have to do is first we have to enqueue 1, we will dequeue 1, and after dequeuing 1 we will print 1, and after printing 1 we will add its child. So we will simply, what we will do, we will enqueue its child. Fine. Enqueue, dequeue, print, enqueue. Okay, this is the steps. So node equals to q.dequeue, code q.dequeue, so it will dequeue. Correct. Then s out, just simply print, sorry, no size of the tree, the system.out.println, system.out.println, and just print the node.data. Fine. Just take care of the queue implementation. Fine. So if node.left is not equal to null, what we have to do is, it's very simple. If node.left, you have to check if left is actually present or not. For the leaf node, you have to check if the left is present or not, if the right is present or not, before adding it. What do you mean by adding it? Before enqueuing it, you have to check. So I am checking it if the left actually is present or not. If the left is not present, we will not enqueue anything. If it is present, then we will enqueue it. It's very simple. Node.left. Okay, and check for this also, for the right one also. If node.right is not equal to null, if it is not null, only in that case we will enqueue. If it is null, then why will enqueue? We will not enqueue. Node.enqueue, node.right. Correct. So this is the same steps that I have just explained you a minute ago. Fine. Done. Now what will happen is, 1 is implemented. So first we will go to 1, key value is 1, it will enqueue key, then it will dequeue 1, it will print its data, then it will see whether it has a left child or not. It does, so it will add it. It will see it has a right child or not. It does, it will add it. So now 2 and 3 are added because the left child of 1 is 2 and the right child of 1 is 3. So 2 and 3 are added. Now it will come again. Now it will dequeue. Now 1 is dequeued from the queue before. So now 2 is at the front pointer. 2 is at the front pointer. So it will dequeue. Dequeue is from the front only. Correct. So 2 will dequeue. It will print 2. Correct. So 2 will dequeue. It will print 2. It will check if 2 has a left child. It does. If 2 has a right child, it does. It will add those childs. As you can see, it added 4 and 5, the left and the right child of 2. Same things for 3. Same things for 4, 5, 6, 7. Now when I went 4, it will check if it has a left child or not. It does not have. So it will not add anything. It has a right child or not, it does not have it, so it will not add anything. It will simply print it. So only these lines will be executed and this if condition will become false. So this is really simple level order traversal. Okay, you just need to have a basic understanding of queue and how to implement dequeue and queue function. After collection, you can use the queue inbuilt queue of Java also. Okay, so this whole code you do not have to write it. Java provides this code. fine. So you can use that queue also, that is not an issue here. Okay, now what you have to do is on the next line, just take a next line and call tree dot level order traversal and pass the root. Now you will simply see that it will simply print the level order traversal, that is nothing but 1 2 3 4 5 6. Also what you can do is just you can see 1 2 3 4 5 6 and 7, and again I have done the same mistake. I have done this mistake so many times now, sorry for that. And you can just print level order traversal, okay. Level order traversal is simply what you have to do is just go here and don't use ln, please. This is the fourth or fifth time I'm doing the same mistake. Okay, so just don't use this ln here. Okay, fine. Now run it, and I think now it will be correct. So 1 2 3 4 5 6 and 7, it is correct now also, but the representation is not that good. So the level order traversal is 1 2 3 4 5 6 and 7. Now everything is over. Pre-order is done, in order is done, post order is done, height of the tree is also done, size of the tree is also done, and level order traversal of the tree is also done. Now you know how you can add a binary tree, how you can create a binary tree, how you can do a traversals on a binary tree using Java. Okay, so this was Java implementation of the basic functions of a tree, of a binary tree, that is the traversal functions, the height of the tree, the size of the tree, and the level order traversal of the tree. Fine, using the queue implementation, and you have to implement this class. Just take care of this one, and the first line that I have written, that array is not of integers but it contains nodes. So you know now, this is a node, key is a node, and we are enqueuing a node, so that array has to be of node type, not of an integer type. Okay, and node we have defined here, correct. So just take care of that in the queue implementation. Okay, so this was the Java implementation for these all methods that we have completed in the past. So these were the Java implementation for these codes, the pre-order, in-order, post-order. Now what I have given you is I have given you some recursion stacks. Now you have to do those recursion stacks, please. Just do those recursion stack, because doing the recursion stack will clear your recursion, and tree needs recursion. Okay, in every step tree needs recursion. Fine, in most of the cases in level order also can be implemented using recursion, so just use recursion. Fine, so just prepare for recursion, just use the, so just what you have to do is simply draw that recursion stack, and it will clear many concepts. Fine, it will clear many concepts. Okay, so if you haven't understood anything, just revise the video again. Okay, it is very clear, it is very easy also, and the code is also not those big codes that will scare you. They are small codes, and they will be clear if you are clear with how to draw a recursion stack. Fine.